So to understand the graphical meaning of or geometrical meaning of these zeros of polynomial, then we are using this tool. You can plot the data or plot the function. There are two possibilities in this one. This is the function and this is the plot from the data. So this is from the table of values. This is from the function. So we can change the function and then we can plot it. And it will give us the information of the slope also. And they can see that these two are the parallel ones. Similarly, I can plot the data, then I am getting exactly superimposed on this line. And then I can change the values here and then I can get another line. So here both are provided, whether you want to plot the graph from table of values or you want to plot the graph from a function. Both are given. Suppose something goes, then you can clear everything and then you can start afresh. Plot data. So data is for plotting the graph from the table of values so that they can compare whether exactly that table of values and function both are one and the same. So the task we can provide for the students is we can give some function and we ask them to get the table of values. So with this tool, we can give them a chance and then they make some trials and then they come up with the values. Here, the table of values can be changed. Suppose this one I take, now I am getting a line. So instead of -1, I go with 1. So I get another line. To -3, 2, 5 is exactly almost, this is parallel, these are parallel. So this tool example usage is given, identify. So any function or any table of values, we can provide them and then we ask them to get the graphs of that polynomial and then where exactly that is intercepting the x-axis and everything they can identify from the graph that x-intercept is nothing but zeros of the polynomial. So that is the actual way. So next we go to the quadratic polynomial. Similarly, we are giving some a general polynomial. You can vary the coefficients and then we can make them to observe the changes it produces. So which coefficient is changing what, whether the shape of the graph is affected or not, whether the position of that particular graph is changing or the shape itself is changing. They can understand through this one and they can see where exactly the x-intercepts are. So we can use this one for exploring any general polynomial and then similarly as before we have this tool. We can give any function here. You can type any function and we can plot it. Similarly, we can plot a graph out of the table of values. So this is almost making coincidence with the plot that we got from the function. So both are possible. You can plot a graph out of a function or out of table of values. So I can go with any type of polynomial, linear polynomial, quadratic, cubic, so there are 4, so everything. So 6 you can have, and you can verify. So we can demonstrate the number of zeros of a polynomial. Suppose for a linear polynomial, I have all the time or the most of the time, I have only one intercept. Suppose I go with 2, then I can see this is pink and the orange one. So maximum 2. I can use this one to measure the zeros of polynomial exactly to locate the x-intercept. Maximum 2 intercepts I am having. Suppose I take 3. So then I can see one intercept. This is the second intercept and this is the third intercept. So 3 zeros of polynomial. So the values I can identify from this. So linear, quadratic or cubic, etc. up to 6 degrees. You can make them to observe zeros of each and every polynomial. So this we are using as the practice of this one. Similarly, we have the relations. Suppose I go with another polynomial x square plus 3x. So by this geometrical pattern observation, we can get the factors of those polynomials. That's a quadratic polynomial. Similarly, we can go for the cubic polynomials. This is exploration, very simple. As usual, this is the coefficients. We can vary them. So we can get the values of this one. Next. This is extra activity we added, and then you can verify whether you can select any function at the properties, what are the roots of it. So possible factors and the standard form. Yes. So you can go with any new function. That's the graph of it. And what are the roots? 1, 2, and 3. This is the factored form. This is the standard form of it. This is the area where if you want, you can use for the teaching purpose. Actually, this is not having any activity of as such. So similarly, the division algorithm for the polynomial. Here you can type any polynomial and then you can search for the roots. Now this is exactly coinciding the given polynomial. Then these are the roots and reminders and everything that will search and provide. Any polynomial we can go with. Suppose I go with just a small modification I made. So this produces any polynomial, we can use this. So what are the different steps of this division of a polynomial? You can have any numbers. Here you have to enter into the 2x cube. 2x go into the 2x cube side is showing. So it is suppose 1 into the minus 16x square. So minus 8. 2x go into 2x. So that is 1. So this is to understand the different steps of the division of a polynomial. So you can have any number of polynomials like this, and then we can demonstrate the different steps involved in dividing a polynomial with another polynomial. This is another method of demonstrating the same thing, but here just you can see by dragging this one and you can understand what exactly this. So I have equal to 2, 1x cube plus 0x square plus 3x plus 2. That so p1 q0 r3. So p q r s. These are the, you can construct any polynomial with by changing the values of p q r s based on the degree. Then you can go with this is the linear polynomial, and then I can demonstrate. I can find out the roots of the polynomial with the help of this. I can select either a equal to 1 or 2 or 3 or 4. Suppose I go with a equal to 1. So this is f of minus 1 is the remainder theorem. Remainder is minus 1 in this case. Suppose I change the value is equal to 3. Now the remainder is 0. So this is how this x plus 1 into 3. x plus 1 into 3. These are all zeros, 0, 0, 0, 0. So this is the 3. Remainder is 0. So if I select a equal to 2 here, so I am having, so whenever remainder is 0, even I can select minus values also. You can make some trials and then try to get the 0 remainder. If not possible, definitely there will be a reminder that we can note it down. So this way we can practice the division of a polynomial by another polynomial. So that polynomial will become one of the factors. So this is how we included few activities for the so again. So it's very simple one. 1 by 2, suppose I consider, and this I take 1. 1. So using this one, we can construct any pairs of linear equations, and then we can visually see where exactly they are intersecting one another. So the f of x and g of x values we can find out which one is greater and which one is less. So what you can do is you can simply, oh, am I audible really?
Yes, okay.
Yes, sir. Audible.
Yes. This is the graphical representation and we have two methods of solving it. Simply drag these lines. Yeah. Suppose. So we have to find out, or if you want directly solve it, you can solve that equation, or you can make some trials before selecting this one. Solution by symbolics or direct solution it provides. So the 3x minus 2 So this dot, and this dot, these three dots we can use, and then we can make them to coincide on that particular lines, and then we get a solution of this where exactly these are coincident. Or you can use this for making it exactly coincide with the dotted lines that are already there on the graph. That's the idea. So because this will be easy when they might have practiced few activities we already shown in the previous polynomials topic, that which coefficient affects the graph in which way. If they practiced it, then that will be easy for them to adjust these coefficient values so that it will make exactly coincide with this one. So here you can have any value for this m. It's not a fixed one. You can have any value for this. Suppose 6 I take, it will alter it. Suppose I can have another value for this b. And similarly, I can have another set of equations by altering the value of this mb, small b, capital M and capital B values. So I have the full control over these coefficients so that I can have one set of linear equations or a pair of equations, and then I try to solve them. You can select this one, or you can straight away play with these coefficients either by using these dots, or you can using these variables or coefficient variation, and you can see here and what is the solution point and everything. Or if you want straight away answer, then you can drag those. Whether it is correct or not, simply select it. If exactly coinciding with the dotted lines, then that will be the answer. So I adjust these dots. So for this activity, the point is that you can adjust, or you can make these solid lines coincide with the dotted lines. Once they coincide, or we make them to coincide, then it will provide as the solution. So that is the simple basic idea of this activity. For getting a new set of new pair of linear equations, you can change small m, small b, capital M and capital B. So you can define a pair of linear equations from these values and then select this one for showing the exact graph of that pair of linear equations, and you alter by these dots or use these coefficients to make solid lines coincide with the dotted lines to have the solution or point of intercept. So this is for the practice. This is like quiz. You can have any number of pair of linear equations. Another point I want to tell you is, if you really want to solve this one by drawing the graphs, then there is a calculated tool that is available all the time. It's very well known. This is a GeoGebra, complete GeoGebra tool, and that will be available. Simply you can go with the function 3x plus 5 is equal to 26. Oh, sorry, 2x plus 5y. Another equation, 6x minus 2y is equal to 4. Now I have two equations. Now we can identify the intercept point. So this is, now they can answer it. So this tool is always available. So whenever you want to plot something or you want to solve those equations, if you are good at using this GeoGebra, then you can directly input this solve command. If you know the commands, then you can directly use solve the pair of linear equations. One equation and this is comma and this is the second equation. Like this, if you enter, then you will get. So this is how you have to enter this command, and it will provide us with the solution. Or you simply plot the graph and then find out the point of intercept. So this graphing method, simply use this tool to plot the graphs and then find out the solution, that's the intercept point. Okay, I will check whether it is correct or not. 2 and 4. So that is correct. Now I can go with another function, plot the graphs and then get the point of intercept and then enter here and verify whether it is correct or not. For the students, what we can ask them is, instead of this tool, we can ask them to plot in the graph sheet and everything. That's from that they can identify the point of intercept. Okay, so in the while teaching, the teacher will use this tool to demonstrate and everything. So anytime this tool will be available. This is the so this is for any general equation 1 and equation 2. You can enter the values and we will produce the graph. And then you can identify the intercept. So this is the one. So you can enter the values of A, B. For example, I go with, suppose I go with 1 and 2. Suppose at which value I want to get. So it finds and it produces a point on this one. Similarly, you can have the second equation. Suppose I have 1 minus 1 x value. I selected 2. Okay, let us see. So I have another point here. I go with some other point. I'm very crude of this, but exactly the points where exactly this point comes anything. So this forms a line. So this is how you can use this tool. So what are the different algebraic methods? So you can enter any pair of linear equations and then you can identify the intercepts or the solution. So how each and every step is explained. And the second, on the right side, you can find out the graphical representation. You can use these sliders to have so you can see how that intercept changes. So we can demonstrate for various pair of linear equations. If they do practice, they can easily understand what pair of equations produces the solution, whether they have solution or not. They can easily identify, but the thing initially they have to practice a bit on this. So what are the different pairs of equations have the solution or not? So this is one, two, three. These are the coefficients of this line, and the blue color. This is another line. This is how that solution got affected. So you can make them to practice for any number of pairs of linear equations and they getting the solution point or point of intercept. So to practice them, this is the one. Substitution method. And this is the practice quiz for elimination method. So this is, if you are good at using the GeoGebra tool, directly you can enter any commands here. The solutions, you can see the solutions of equation. So you can enter any number of pair of equations, one equation, comma, and the second equation, then it will give us the solution. So if you want, you can use this tool for getting the solutions of pair of linear equations.
Sir, Sharma sir, not getting
Yeah.
your voice.
Is it okay now?
Yes, sir. Yes, sir.
Yeah, sorry. Okay. So I think a bit disturbance in the network. So is it all right? Hello?
Yes, sir. Now it is okay.
Yeah, okay. So here you can define any pair of linear equations and then it will produces the solution. That's it's not that's an extra activity that we provided. Yeah, up to now, any more information, sir? Anything? Just I'm quickly going because of the time that factor and everything. I'm not going into much detail of these things. Just I'm showing how exactly, what exactly these activities, only that much. And most of the other information, what exactly we can do with these activities and other questioning and everything already available in the workbooks. I think you might have received that one. So this is for the quadratic equations. Just quickly I go through this. It's already demonstrated. These are the change of the coefficients which produces the changes. That the only demonstration we have. And this is, yeah, what are the zero factors of the polynomial? This is a bit of small explanation of this one. Then what is the activity connecting this? Yeah, this is the practice. Once again, we are connecting a quadratic equation in with the graph. So what is this 2 is nothing but this arrow represented in blue color, this 2 represented by this arrow. We can drag and change the arrows and it produces a quadratic equation, so that the student can understand how this quadratic equation can be understood. Suppose I drag towards this one. So we do produce a lot of quadratic equations by simply dragging these 2 points, and then we make the student to observe the pattern of changes, how the changes are produced. If I drag towards this side, whatever this -2 I am getting here, +2, x +2. So this x plus 2 means it will be on the left of the y-axis. If it is minus 2, it will be right of the y-axis. So these observations, they will see, the student will see these pattern changes, and then they will identify the equations very easily. So for the same thing to practice, we are providing some quiz-like thing. So the same thing, the thing is that here we give them some quadratic equation and we ask them to arrange this graph exactly representing this equation. So y minus 4 of x minus 4 whole square plus 3. So if they practice this one, if they practice on this, then they can easily identify the graph of this and how to, what exactly this 3 into x minus 5. Minus 5 is there means it will be on the right of this. 1, 2, 3, 4, and this is 5. So this plus 5, 1, 2, 3, 4, 5. This is 3, 1, 2, 3. Okay, let me check whether it is correct or not. So this is the correct one. Like this, they will practice any number of quadratic equations and their graphical representation so that they can understand the coefficients of quadratic equation. Thereby it helps them in understanding or finding the solutions of such things. So they will practice any number of problems we can produce in this one. So that is for practicing quadratic equations and their graphical representation. So the different forms and what are the different steps of solving a quadratic equation. These are the steps. So how we do it. Select a new equation, convert into a standard form. And these are the factors. We can demonstrate the solutions of any number of problems. Standard form. And these are the factors. Zero product rule and the solutions. This is to demonstrate the steps of solving. Okay, suppose if I want to find out a solution, not by any numerical thing, but we can use this activity. Suppose x square is there, that x square is represented by, this is the one. This is called algebraic tiles. Simply by arranging these tiles, we can get a solution of this, are the factors. Because I am having x square, this is one block representing the square. I have 8x. So these are called x blocks. I can select 1, 2, 3, 4, 5, 6, 7, 8, 3, 3, 6, 1, 7, 8. So I can find out the possible number of ways. Suppose I go with this one. So I can have multiple ways of arranging these 8 x tiles. This is one way. Or I can do another way. I can remove here and I can put vertically. I can stack vertically. This is another possibility. And this is another possibility. But I have 1, 2, 3, 4, 5. So how many numbers I need to fill? 5 into 3. If I select this way, 1, 2, 3, 4, 4 into 4, and a 16 I need, 16 single blocks. 1, 2, 3, 4, 5, 6, 7, 8. So I can arrange these tiles like this and fill that area. So 4 into 4. So is it possible to get a solution for this or not? We can see x square plus 1, 2, 3, 4, 1, 2, 3, 4, 4x plus 4x, 8x plus 12. But I'm not getting 12 here. I'm getting 16 or 15. This way I cannot get a solution. But I have another arrangement. Suppose I have arrangement like this. 6 plus 2, 8x. Okay, that is good. Now I have Now I have 1, 2, 3, 4, 5, 6, 6, 12. So this is the constant term. X square plus 6x plus 2x plus 12. So initially they will go with some trials and they will arrange these tiles in a proper way. They start with 8 along horizontal stacking, 8. Then they remove 1 and move it to the vertical side. And then they move it and they can fill this one. And now I have, this is x, 1, 2, 3, 4, 5, 6, x plus 6 multiplied by x plus 2. So now I have a solution of x plus, this is x plus 6 and this is x plus 2. Now I factored this given quadratic equation. X square plus 8x plus 12 is equal to 0. So simply by arranging these algebraic tiles, these are called arranging the tiles. We should remember that this is representing x square block. This is minus x square block. This red one represents minus x square. This is plus x. This is minus x. This is plus 1. This is minus 1. And the student will identify the number of possible ways of arranging these. Which one is exactly producing this one, they will identify. Here I am getting. If I change or alter this one, if I move it like this, but I cannot get these 12. Now in this case, I am having 1, 2, 3, 4, 5. 5 into 3, 15. So if I have x square plus 8x plus 15, that is also having a solution. But the solution is different. Now, what is the solution? Here it is. Now the solution is different. Here I am having x plus 5. Here it is. Now I have x plus 5. Here I am having x plus 3. So they remove 1 and they will shift to the vertical side. And then they can see that x plus 4 into x plus 4. X plus 4 into x plus 4 is a perfect square. So which one will become perfect square? X square plus 8x plus 16 will become a perfect square. Like this, they will practice more number of quadratic equations and then they can identify the factors simply by arranging these tiles. And this is the practice activity so that they practice more number of quadratic equation. This is simply to practice. Another way of representing it, they will fill up with which one is this one. Suppose I go with x plus 1. This is the trial and error method. Suppose I go with x plus 1 into x plus 1. Or you can select the hints, sum of factors and product of factors. Or I can go with some trials. Suppose I go with x plus 2. Whether exactly I am getting this quadratic equation or not, I can see. Once they practice by trialing, then they can identify through the patterns, they can identify directly the solutions, or they can predict what exactly or what may be the solution straight away. But the thing is, they have to identify, they have to observe the patterns, how that is affecting or how these factors are producing the quadratic equations. So one I take x plus 3, this x plus 4, and x plus 5. So what are the different quadratic equations I am having with x plus 9? So we can make the student to practice on this one. We keep one as constant and another one is the varying one. Then I can demonstrate. Suppose, is it possible to produce this one? So 50 I want to have. So the maximum is 10. So now I go with what happened? Yes, now. So initially they go through the trial method and finally they come up with the correct solution. So any number of problems we can give for the students to practice and identify the factors of that one. Now this is the method of completing the squares. Yeah, this is the visual representation, and later we can.
Alexa, what is my phone's battery level?
Oh, hello. ఓనా సార్, నాకు ఇదే ఈ ఫుల్ స్క్రీన్ లో ఉన్నాను, నాకు అడ్మిట్ అరే
సార్
అవునా, అవును సార్, రైట్ సార్, ఓకే సార్, సారీ, నేను ఫుల్ స్క్రీన్ లో ఉన్నాను సార్, నాకు కనపడట్లేదు అది, జస్ట్ రైట్ సార్, రైట్ సార్, థ్యాంక్ యూ, రైట్ సార్. తేజ,
సార్ ఇప్పుడే చూసాను.
నేను ఇదే ఫుల్ స్క్రీన్ లో ఉన్నానా, ఇది పక్కకి వెళ్ళిపోతుంది నాకు,
సార్
అందుకు కనపడట్లేదు. ఇది ఆటో లాగిన్ ఎక్కడ ఆప్షను?
అదే సార్, కొంచెం ఒకసారి జూమ్ సెట్టింగ్స్ లో చేంజ్ చేయండి సార్, ఎందుకంటే నాకు
yes sir, I'm selecting it, sir, I'm selecting it.
Okay, sir.
Okay. More options. ఎందుకంటే ఇవి సైమల్టేనియస్ గా కనపడవు సార్, ఇందులో స్క్రీన్ షేర్ ఫుల్ స్క్రీన్ లో ఉన్నప్పుడు ఇంకా ఇవన్నీ కనపడదు.
అదే
పార్టిసిపెంట్స్ మోర్
వెయిటింగ్ రూమ్ తీసేయండి సార్.
వెయిటింగ్ రూమ్ లేదు సార్, ఇది ఆటో లాగిన్ ఆప్షన్, వెయిటింగ్ రూమ్.
ఒకసారి స్క్రీన్ స్క్రీన్ ఆపండి సార్. లేకపోతే
ఇక్కడే ఉందా? ఇక్కడ ఉందిలేండి సార్, తీసేసి. ఇక్కడ సెక్యూరిటీలో ఉంది సార్, అది ఎనేబుల్ వెయిటింగ్ రూమ్ ఉంది కదా, తీసేసాను ఇప్పుడు. దెన్ యూ కెన్ డైరెక్ట్లీ కమ్ హియర్. యా, నేను పుట్ ఓకే. ఇంకా ఏమైనా ఆప్షన్ ఉందా సెక్యూరిటీలో? Chat rename and let's start video. Okay, sir. I think that will works out.
What did we say? Yes, we already. What did we say?
So I disabled the waiting rooms and directly you can. Now you can directly join. Waiting room is removed. Teja, is my audio okay?
Okay, okay, sir. Continue, sir.
Okay,
Yes, sir.
okay.
Yes, sir. Okay. Did you watch the previous one, sir? Okay. Anyhow, we have the same thing here also. This is the visual representation of the primary point of this one is we are converting whatever that numericals into the geometrical pattern. That is the basic idea. And simply you can change the coefficients by sliding this one. And if you want to visually see how that builds out the geometrical form, this is how it produces. How many number of squares that are left? 1, 2, 3, 4, 5, 6, 7, 8, 9. So simply slide it and then observe. So what is the question mark that we can answer? So yeah, the question mark is nothing but 3.
కంపెనీది ఏదో రిజిస్ట్రేషన్ అవ్వమని చెప్పేసి పెట్టాడు అనమాట. టైం అయిపోయింది.
3 into 3, that is 9. 9 tiles means here I have, if I take 9, this will become definitely a perfect square. Because this is x plus 3, this is x plus 3, x plus 3 into x plus 3, that will become perfect square. So if I want to make this one as a perfect square, I need 9. So how this builds out? Suppose I change like this. Will it become a perfect square or not? This is a perfect square. 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 They can observe the pattern. Suppose this is the negative value. This is for the positive value. This is the perfect square, x square. Next one is, if this constant term is a perfect square, suppose this is 1 means 1 square. Okay. Now I have 2 means 2 square. 2 square, this is 4. Okay. Now I have 3 square, that is 9. So if the final or the constant term is a perfect square, definitely we will going to have a perfect square based on this number. If it is possible to have this one. Okay, 3 plus 3, 6. So this is 9, x square plus 6x plus 9. So I can show the next one, 4 plus 4, 4 into 4. 4 into 4, 16. 4 plus 4, 8. So x square plus 8x plus 16 is the perfect square. And another one is 10 and 15. 25. 12 I have. So 1, 2, 3, 4, 5, 6. 6 into 6, 36. The next one is 49. Next one is 8 square, 9 square, 10 square, 11 square, like this we get. So whenever I want to have a perfect square, the simple idea I can have in my mind is I will be looking for this constant term, and if it is possible to make it as a perfect, or is it a perfect square? Suppose I have a 2 as a constant term, so it is not possible, that one 2 square is not there. Or 1, 4, 9, 16, 25, etc. If I am having constant terms like that, then there is a chance of having or converting this one into a perfect square. That is one. Still, if you want more visual information of this one, then you can have any construction of any polynomial and then simply watch it, how it builds out. and how many squares it left. So simply sliding this one. And the same thing, if I convert that one into a square, the graph, then how I get? Slide it, build the geometry or a perfect square, and this is the complete square, whether I am getting a parabola or not, because squared equation or quadratic equation should give us the, yes, this is 3 and this is 9. This is graphical representation of the perfect square. You can change any other one. You can see 1, 2x. I go with the negative values also. So this already we practiced in the beginning itself, how to represent a quadratic equation by a graph. It is nothing but a parabola with two coefficients representing this one and this one. This represents what and this represents what, we already demonstrated. Because there is only one coefficient of this x square as only one, we don't have any multiplication factor. So you can alter the middle terms at the coefficients and then we can demonstrate. So this is the correlation between this perfect square and this graph. Both we can demonstrate visually. And the same thing, how we can give the student the activity. How we can make the student to arrange the tiles. As the previous one, then we can, this is the x square plus x square, this is minus x square plus x minus x, this is 1 and 1. Each one is a square. These are called the algebraic tiles. Suppose I want to represent this x square, then I can use this tile. This is x square. How many x I have? This is 12. 12 in number. Now I go with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So how many ways I can arrange these 12? Suppose I start with so horizontally I arranged 6. Vertically also I can arrange 6. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. So how many ones I need? Then I can fill it out. Arrange them properly. And they can, without filling also, I can identify how many are needed to fill this area. Or otherwise, I am just showing it out. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 6 into 6, 36. So x square plus 12x plus 36 is a perfect square. Here for this one, I have x plus 6. X plus 6. For this one also, I have x plus 6. So not only this one, they can explore other possibilities. Suppose if I rearrange this one like this, will it become a perfect square? So is it possible to have a perfect square? Will it become a perfect square? But it is not, because this length will become x plus 7. This length will become x plus 5. So this is having larger distance. Suppose if I consider this one as the geometry, so it is not a square, it will become a rectangle. So it is not a perfect square. So geometrical square can be represented with a perfect quadratic equation or a perfect square. So what we are doing here is equation is getting converted into a geometrical form. So by this way, we can make the student understand the patterns. If they find a square, geometrical square, then they can understand that that can be represented by a quadratic equation. What type of quadratic equation? Suppose the length is 5, that 5 square will become. So 5 square is 25. This is the constant term. This determines the perfect square, whether the equation is a perfect square or not. 36 I am having. Suppose I have 30, so it is not possible. It may be having a solution, but it will not be a perfect square. So they will identify that way. Or if you want a new problem, you can generate a new problem, and then we assign that problem, and then we ask the student to arrange these tiles, and then we ask them to get a perfect square. Is it possible to convert, or we can ask them to convert a quadratic equation into a perfect square by adding something or deleting something. They can easily identify that one. So this is the complete activity for understanding the perfect square nature of that one or not. Okay, that's method. And this is the activity. You can demonstrate any quadratic by changing these values, and then demonstrate the nature of roots. So the full screen is available. Similarly, we can demonstrate the same thing by the graph b square minus 4ac. So for that, how the graph looks by changing the values of b or c and a also. B square minus 4a. See how that value changes and what is the shape of this graph, then they can understand. So if they have a graph like this, then what may be the discriminant for that particular shape of the graph or not. So this is just demonstrate the nature of the roots by selecting A, B, and C values. Same thing, but graphical representation of this one, b square minus 4ac. This is a practicing quiz for them. You can generate any quadratic equation, and you can, after doing, you can select the solution. This is for getting any number of equations and verification of the answer for it. So now I quickly move to the next one, and the arithmetic progressions. How we connected this one, arithmetic progression. And here also, once again, the thing is that for getting an idea what exactly this one, suppose I start with, once again, we are using the same square tiles for representation of the numbers. Suppose I have 3, I'm using the 3 unit squares, and I can ask the student in how many ways I can arrange them. So this is one way of arranging. This is another way of arranging. This is another way of arranging this. Suppose I ask them to arrange these three in two columns. And what is the possibility? If I arrange them in two columns, this is the possibility. If I ask them to arrange them in three columns, this is the possibility. But I go with the two columns. Now, what is the difference? This is 1, this is 2. What is the difference between the two? That is 1. Suppose I want to arrange with the next number, which is having the same difference of 1. So how many tiles I need? I need 1, 2, and 3. So 3 more I need. So 6 I am choosing. Now I can add third column with 3 tiles. Now I can ask them, what is the difference between this one and this one, this one and this one? This is the successive difference or common difference it is called. And even I can demonstrate their linearity simply by drawing a line connecting all these vertices. Wherever I connect, whatever it may be, it will connect by a line. Oh. I can remove. If I want, I can remove this one. Suppose I want to arrange the another column with the same difference. So how many I need? I need 4, total 10. So they will observe the pattern. 1. Oh. Where this gone? I said this. Somewhere it gone. Okay, I reset it. Then I go with. So this is how we can convert, and 1, this is 2. This is one possibility of arranging all these 10 numbers with a successive difference of 1. Suppose I want the difference of 2. Now this is the possibility. So I have 1, this is 3, and this is 5. 1, 3, 5 with a difference of 2. Whether I get a line or not, then I can verify. So definitely these are all the linears. So these tiles I am using for the representation of the numbers. This is the stacking of these tiles. By using the stacking of tiles, I can demonstrate the progression, how the column is progressing, or how the next number, or what may be the next number I can. So simply I will select, oh, it is getting removed. Suppose I have 40. So I can have any number of tiles here. Suppose I want 100. So 100 tiles I can. So like this, I can have any number of tiles, and then I can give an assignment or the task to stack all these tiles into a particular pattern. So that pattern they will see, and they can convert into the numbers. They write the numbers of that particular column height. So this I am using for demonstrating the progression. So how I am increasing or how I am decreasing the column height. So column height represents the progress. What is the difference between the first column and the second column, and the third column, fourth column? So if that difference is constant, then it is called a common difference or constant difference. If that is constant, then that progression is called arithmetic progression. So by geometrical arrangement, we can make the student to practice the numbers, how they are increasing or decreasing, or how they are progressing in a particular manner. Suppose the same thing I can use for finding the nth term of an AP or other one, because from the previous activity I came to know that the progression can be converted into a line. Now I am using the same thing. I can have set of values. If I am able to plot these points on a graph, if I get a straight line, definitely that should be a arithmetic progression. So how I connected that straight line, or what is the straight line and the arithmetic progression, that is the relation. So how this can be represented as a straight line. A is equal to 0, D is equal to 1, N is equal to 12. So I can have, suppose at 13, what is the number? 14, 16, 17, 18. So 21st, 23, 24, 26, 27, 28, up to 30. So 30th. So the formula that we are using is Tn is equal to 0 plus n minus 1 into 1. This is the one, because I am getting Tn is equal to a plus n minus 1 into d. This is converted in or compared with the straight line that is plotted on this graph, and then we can extend towards the negative side or the positive side to any number. And I can change the d or the common difference. Suppose I go with the 2, common difference 2. It is comparable with the slope of the line. Suppose I have 1. This d is nothing but are acting like a slope. So I have 5. So d value is nothing but the slope. So from the slope we can find out the relations. This is for the negative values of the d. This is for the positive values of the d. And we can demonstrate how this initial term alters this line. I can find out any term on this or from this graph. I can reset everything. So what we did is, in this activity, we converted that formula into a graph. That graph is nothing but a straight line. So this arithmetic progression is always a linear progression. It is not polynomial or exponential or quadratic or anything. This is simply a linear progression. That is the reason why that difference is always the same, or it is called common difference. This is simply a practice quiz. Once they are good at identifying the patterns, then they can easily answer this. So each time we can have a new problem. And here, this term, the student has to identify. How easy to identify? Once they are good at observing the patterns or the changes. There is an easy method of identifying this one. Just one way I will, and we can ask them to identify the difference of these two and divided by the gaps between these two, and then they will add the same thing here. Number of gaps multiplied by that difference. So 1, 2, 3. They will find the difference between these 3 divided by 3 and that one multiplied by 4. Whether it is a positive side or negative side, they can identify. So that is one way of getting the required term in this particular progression. So they can practice any number, or you can follow any other methods of getting this one, or you can directly apply that formula and then they can find out. So this is a quiz like thing. What is the sum of n terms? How we can observe or how we can convert this one. This is the usual way of representing this one using that formula. Sn is equal to n by 2 into a1 plus n1 n minus 1 into d. But the similar thing, we can convert that progression into a geometrical pattern. And this is how I can increase the number of terms. Suppose I want to get the sum of 2 terms, n equal to 2. So half into area of that geometry. So this half into area is exactly the required sum. Suppose I can increase n equal to 3, n equal to 4. For simplistic nature, I can go with, start with 1. A is equal, a1 equal to 1. This is 1. D, I start with 1 itself. So this is A1. A1 is 1. 1 plus AN, 1, 2, 3, 4. So half of this area. This is A1, this is AN. Half of this area is nothing but sum of n terms. You can observe by changing 7, 8, 9, 10. So this method simplifies or makes the student to visualize what exactly the progression looks like, a summation. How to find out the sum of these terms. And now I go with common difference 2. How it changes the geometry. They can see the pattern. Yeah, slowly I am increasing the common difference. So up to 5. And I can change the number of terms. 2, 3, 5. So this length is known, this height is known. Simply they can find out very easily the area, length into breadth divided by 2. If that is converted into a formula, n into a1 plus an by 2. N is known, a1 and an both are known, then they can easily find out. So either geometrical representation makes them to visualize it. So this is a practice quiz. You can produce any number of problems with this one, and then we can make them to practice any number. This is regarding the sum of n terms. So that ends that. Now I quickly move to the triangles. as usual, this is the basic info, what exactly the angles are not. So similar figures.